This is our last numerical method. So numerical methods have included so far using rectangles. That would be like the midpoint or left or right endpoint or anything in between. And then you curve the top to get a trapezoid with a straight line. Okay? Now, what if the top part was not a straight line segment, but actually curved with the curve? Does that sort of make sense? Like you had your f of x, and then you had your 2 points, and you connected them with a straight line. What if you connected it with something that actually curved to follow the function in some sort of way? That's what Simpson's rule is. Instead of connecting the 2 points up at top, like f of x0 and f of x1 with a straight line segment, we're gonna connect it with a piece of a parabola, basically. So parabolas, they have some innate curviness to them, right? So if your function has some curvature to it, that top part now follows it even better. Is that making sense so far? Okay, so this one does work better than the midpoint rule. It is like one of the better numerical integration methods out there that's like simple enough to teach in a first year calculus course. Numerical analysis courses would cover more advanced like methods of doing it, and you can like have like more fancy curves. So this sort of makes sense basically that there's other ways to do this. Like we're going up the progression. We started with a flat top, and then we had like a flat thing that followed the curve, and now we actually have like a curved piece that follows it. So in a moment, I'm gonna change over to our writing mode. I'm just setting up the screen. It's going super slow. There we go. Okay, writing. Wrong one. There we go. Okay, so we've got Simpson's rule. Boom. So the idea here is, let's draw the picture, insert graph. Let's say you've got, how should we draw this so it looks sort of like it makes sense? Let's just draw it like that. Okay, and you're gonna go from A to B, and let's just do it with, split it up twice. So x0, x1, x2, and x3. And you can sort of see why this makes sense. Like, why am I only doing it with n equals 3? Because if n was equal to 3, what would your trapezoid look like? It would look like this. It would look like this, and it would look like this. So see how with the trapezoid, the first one, it would go under. The second one would be pretty good because you see how it's just following it. But then this one over here, it's not following it so well. Now you can see from the first one and the third one why you'd want something that has a curved shape that would follow it well, basically. Because Simpson's rule is going to connect it to look like that. It will follow it sort of decently. It will collect it to follow it like that. And then it would connect it to follow it like this, which is basically more or less what you want. Okay, so when we're dealing with Simpson's rule, Sn, right? So you're going to say how many curves, right? The S stands for Simpson's, like T stands for trapezoid, M stands for midpoint. So let me write it down. It works like this. Okay, that's the trapezoid rule. Where did Simpson's rule go? It's like disappeared. Okay. So Simpson's rule is delta x over 3 times f of x0. So the first one, no change. And then 4 times f of x1 plus 2 times f of x2. And then what you're going to do is you're going to keep on repeating 4, 2, 4, 2 over and over. Any term that has an odd xi, so x1, x3, and so on, will be times 4. Oh my god, my brain just like died there for a moment. For any xi term that is even, you're going to multiply by 2. So I'm just going to put plus dot 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 4f of xn minus 2 plus 2 times f of xn minus 1. And then your final term is just f of xn. I guess let's just sort of lasso this and move it over to the side a little. Okay, we'll just move it down. There we go. Okay, so notice it keeps on repeating this pattern of 4, 2, 4, 2. Okay, now this is going to be useful for us if we're going to do this in Wolfram, to notice that the odd terms are multiplied by 4 and the even terms are multiplied by 2, so we can do sums of the odd ones versus the even ones. I want to point out that if you want an odd number, that's 2n minus 1. If you want an even number, that's just 2n. Okay, because that's what we'll use as our index to do this. Okay, and then I guess I also need to point something out. Only certain types of n's will work for this. If you do f of x0 plus 4f of x1 plus 2f of x2 and then 4f of x3, and you wanted to end on x4, do you see how that's not going to work? Because you need 2f of x4 and then an f of x5. So this only works if n is an odd number. Because pair of 4, 2, pair of 4, 2, the first and the last one are a pair. Oh shit, wait. Yeah. There we go. Sorry, I caught myself for a second. I was like, wait, what am I saying? Yeah, n has to be an odd number. Zero, 1, 2, 3, 4, 5. Yeah. Oh, that's weird. Why does the book say that it needs to be an even number? Am I counting wrong? Zero, 1, 2, 3, 4, 5. Oh, shoot, my bad. I'm so sorry. N is going to be an even number. What's weird about this... Sorry about this. Is that what actually happens is that your last one here, sorry, just ends with a 4. And then you get f of x4. Sorry, I read it wrong. So you have pairs and then there's a final 4. And then you have your last one. Oof. This always throws me off when I talk about it. It goes 4, 2, 4, 2, 4, 2. There's a final one with 4. Then your last one. So it does end as an even number, and actually, okay, I need to go back and fix this. I screwed that up, my bad. Okay, let's look at it. It will look like this. It will come in pairs. And then there will be a 2f of x n minus 2 plus for f of xn minus 1 plus f of xn. There we go. There we go. My bad. Sorry about that. So they come in. Does that make sense? They're gonna go in pairs until this last one, which just has the 4, and then you get your final term. That's why you end on an even number only. Oof. Okay. If so, you're saying like if n equals 2. Okay, almost. Okay, so let's write n equals 2. You get f of x0 4 times f of x1 plus f of x2. You always have to have this single ending 4 before the last one. So there's 0 pairs here. And now what's the next one going to be when you do n equals 4? It's going to be f of x0 plus an actual pair, f of x1 plus 2 f of x2. That's a pair. And then you get a singular for f of x3 plus f of x4 before the last one. And then you would so then it increases by pairs of 2. Yeah, weird, huh? This always throws me off. Yeah, and it's because there's a single one and then they add in pairs afterwards. Okay, so let's do an example of this. So example, let's do S6. Simpson's rule was 6. To estimate the length of the curve, just like last time, y equals 1/2 x squared between x equals 1 and x equals 4. So remember how we did the arc length estimation before with the midpoint? Okay, so now because we're doing it with S6, so first of all, let's set up our integral. We're finding the arc length from 1 to 4, the square root of 1 plus y prime is just x, right? So you get 1 plus x squared dx. So the function that we're actually estimating is f of x equals square root of 1 plus x squared. Okay, our delta x is going to be b minus a over n. Our n is 6, so you get 3/6, which is a half. Okay, now you need to find out what your xi is. Your xi is a, which is 1, plus delta x, which is half. So that's going to be 1 plus I over 2. Okay, and now you just need to set it up. S6 is going to be delta x, which is 1/2, divided by 3. So that'll be 1/6. I'm just going to write that that's the 1/2 divided by delta, that's the delta x divided by 3, right? Delta x is half. Half divided by 3 is 1/6. And then what are you going to have? F of x0 plus 4f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus 4f of x5 plus your final f of x6. It's a lot, right? It's like, holy shit. Okay, let me put that on one line, actually, so that it looks nicer. So I'm going to lasso it. Should be that too. Okay, cool. So let's just put that down here. Okay, and then let's move this part up here so it's all in one line. Okay, wait. I like ran out of space. There we go. There we go. Now it's all in one line, right? That's like easier to see. Okay. So we're gonna plug this into Wolfram, and to help ourselves a little, we're gonna set up some sums. So what are the things that we need to pair together? Everything with a 4, right? We could write 3 of them separately, or we can write a sum to pair them together. And then we want to pair these two together. Okay, making sense so far? Okay, now what you need to do is figure out your starting and ending index. So the things with the 4, they're odd, right? So that's 2n minus 1. Now, what is your starting number? x1, right? So 2n minus 1 needs to be equal to 1. If you solve for n, you get 2n equals 2, which means you'll start at 1. Okay, now what's the ending point for that? 2n minus 1 equals, the last one is x5, so you're going to set that equal to 5, which means 2n equals 6, which means n equals 3. So what have we found out? For the ones with the 4, you're going to do the sum of 4 times f of xi, where your I goes from 1 to 3. As opposed to writing them individually, that sum statement spits out those 3 terms. Okay, now you have to do the same thing for the other one. They're even numbers, so you're going to use 2n to generate. Actually, whoa, let me fix this. Sorry. Let me show more how it's going to be written in Wolfram. You're going to want 4 times f of x of 2n minus 1, where the n goes from 1 to 3. There we go. You need to actually put that 2n minus 1 index in there. I forgot to write that. Now for the other one that's even, you're going to use 2n as your index. And what's the first number that you start with for those? Do you see how you have x2? So you set it equal to 2. So you have n equals 1. And then what's the last one? N equals 4. So you set 2n equals to 4. And you get n equals 2. So for that one, you're going to have the sum of 2 times f of x of 2n, where the n goes from 1 to 2. So I'm going to pause and leave that there for a moment. Because really what you're doing is just finding the beginning and ending index to add up those odd terms and to add up those even terms. So you just set your 2n minus 1 equal to the start and the beginning. At the start one's always going to be 1. I'll just tell you that. You really only need to solve for the ending one. You'll always start at 1 and end at 3. You'll always start at 1 and then you set the ending one, and that's the number that goes there. And I guess, yeah, that works. Okay. So let's go and actually plug this in. Holy crap. It's a lot. So I'm going to change over to Wolfram. Okay, so what was our f of x that we're actually estimating? I think it was the square root of 1 plus x squared, right? Yes, I'm looking back up. That's what we're estimating. Our delta x was 1/2. And And our xi is 1 plus I over 2. Yay! Okay, cool. Okay, now our sum is 1/6 times, now in parentheses, you have your f of x0. You have your f of x6. Those are your first and last terms, right? If you look in your notes, you'll see, or what we had earlier, you have the first and last terms. They aren't multiplied by everything. Now you have that other stuff in here, right? The things in here are going to be the odd terms and the even terms, right? Okay, now we found out the formula for the odd terms. The formula for the odd terms was the sum of 4 times f of 2 times n minus 1, where your n went from 1 to 3. And then what was it for the even terms? A very similar statement, except for instead of multiplying by 4, you multiplied by 2. Instead of having 2 times n minus 1, you just had 2n. That's what made those terms even. And instead of going from 1 to 3, you went from 1 to 2. Boom! And actually, look, it even spits out all the numbers that you would get if you calculated all the terms by hand. Do you see how here's f of x0, f of x1, f of x2, f of x3. Okay, it simplified some of them, f of x4. So there must have been some repeats that simplified. And as a decimal, you get 9.49. Which, let's see how that compares to the integration. If you wanted to integrate f of x, x going from, what was it, 1 to 4, I want to say? Yeah. According to this, the exact, oh shoot, that's like off by a lot. I think I scooped something up. Oh no, this is not good. Oh! I forgot to do f of x of. If you go back and look at the notes, it's not f of 2n minus 1, it's f of x of 2n minus 1. It's f of x of 2n. Okay, now let's rewrite. Okay, there. Now you see the 3 terms, or the 6 terms, right? F of x0, f of x1, f of x2, f of x3, f of x4, f of x5, f of x6. And then you rerun it and you get, oh, there, 8 point, okay, there, now they match. So you can see with an estimate with 6 on Simpson's rule, it only disappears in the tenths, hundredths, thousandths, tens of thousandths place. So that's like pretty close. Okay, I know that this might look a little confusing with you doing these sums for the odd and the even terms. It ends right. This is the whole problem. The problem starts right there. Oh, my bad. Oh, I see. There you go. Is that better? No problem. So I'm gonna say this. It probably looks like a lot of work to sort of figure out how to set up those sums for the odds and the even ones. In the long run, however, it will save you hours of time if you learn to use the sum thing to set up those repeated terms as opposed to just typing them in by hand. Can I just quickly show you what it would look like if you had to type it all in by hand, and hopefully you'll see like why it's useful to learn how to do this. You would have to like literally go in here and replace all that with 4 times f of x of 1. And then you'd have to do 2 times f of x of 2. Okay, and then you'd have to like keep on copying and pasting that in there, which is going to be sort of a pain. Plus, okay, then this one would become 3, and that one would become 4. And then plus that final 4 times f of x to the 5th. I mean, I guess that's not that bad, but I hate doing this. I would rather set up the sum so I know that here's the odd terms and here's the even terms. Because, like, I don't know, I just hate having to write stuff out like this. I mean, I guess if you really wanted to, you could. Does everyone see the difference between this one here and that one there? And the bottom one, I've literally just written out all the terms. In the top one, I wrote code so that it expands, it makes it for me, basically. You can always just do this one. You'll see if we run it, we get the same exact thing. Alright, do you see how this matches literally? Oh. It should match it. No, here I am like saying it should match it, then I get like something different. Let's see if it's the same. Okay, I must have typed it in wrong. What's going on? Oh, thank you. Okay, there we go. Oh, no, they're still slightly different. F of x0. See, this is why I hate doing this, because it's easy to make a mistake. 4 f of x1, 2 f of x2, 4 f of x3, 2 f of x4, 4 f of x5, f of x6. I made a mistake somewhere. I know that the first one was actually the right answer. It's the funny thing. This one is wrong. This is why I hate plugging them in by hand like this, because like there's somewhere where I screwed up like an addition sign or a multiplication sign, and I can't even find it. That's why this is bad to type them all in. I'm not even sure what's wrong with it. Which is why I highly recommend you do it this way. Yeah, this one? You mean this one where I actually have it do the 2n minus 1? You have to put it in yourselves and come up with what the numbers are, yeah. The 2n minus 1 is what you use for the odd terms. The one with 2n is what you use for the even terms. And then you have to figure out what bounds are here, like what I explained earlier in the video. Which is why, like, even though it's time consuming to do that, I find it better than trying to type it in like what I did right here, because I made a mistake typing it in, and I honestly cannot find right now where the typed mistake is. Yeah, right. No, that's the thing. Like, because it's hard. Like, if your finger slips in one little place and you just don't notice it, like it's sometimes it takes like a good 5-10 minutes. I've had things where like I typed them in like this and I spent like an hour trying to find it, and then I only realized at the end that like there was one little thing off somewhere. It's much easier with this one to do it. Oh, it's sad. But yeah, it's close, but it's not the right answer. Like, we're supposed to get the 8.14594. But for this one where I typed it all in, we're getting 8.47928. And yeah, I don't even know what the problem is. Hey, if we run it again. No, yeah. 1, 6 times f of x0, 4 f of x1, 2 times f of x2, f of x3, f of x4, f of x4 times f of x5, f of x6. It should, yeah, it was supposed to give me this number, but it's not, so.